All right, this is lesson 6.1. I'm going to go over the key with you real quick. I'm going to go over it kind of quickly as I'm going over it. If you have any questions, please write them down because you're going to have a chance to ask questions on the feedback form. What you're going to need to answer on the feedback form is how many questions on this assignment did you leave blank? There are 20 questions. If you didn't do any of it, you left 20 blank. Please be honest and answer that. I need to know. I might be disappointed, but I'm not going to be mad. I need to know who was unable to do the assignment for whatever reason. If you were able to do it, I need to know how many you got correct and how many you got incorrect. Again, there's 20 questions. Those numbers should add up to 20 because they're one or the other. They're either not done or they're done incorrect or done and incorrect. You're also going to have to tell us 2 things that you learned on this assignment. And then again, log down any questions you still have so we can answer those when we come back to class. All right, first one. This is all one question even though it's 4 parts. You just have to put it in standard form. That's listing the highest power of x first and then descending the leading coefficient. The leading term is the highest power of x and then the coefficient matches to that. The degree matches to the highest power. And then finally plugging in a -2, f of -2. When this is f of x, you're going to replace every x you see with a -2. Be careful on those negatives. It should evaluate to -97. Remember, if you cube a negative, you get a negative. If you square a negative, you get a positive. So be careful with those. Over here, and we might have to go over these again. I'm going to talk about them really quickly, but I didn't talk about them a lot in the notes either. These were graphing parameter changes on the parent cubic function. I did not do a table for number 2 because it's simply the parent function shifted to the left 2 units. Parent function left 2 units. You have to know what the parent cubic function looks like. This one had a lot of parameter changes, an A, an H, and a K. Remember, A and K on the outside affect your Y values of your parent. Here's the X and Y's of the parent. Parent x cubed, Y equals x cubed. So I'm going to take every Y value of the parent times A is -2 and then add 2. The stuff on the inside affects the X's. Insiders lie, you do the opposite. You can see -1, you're going to add 1 to the X's. Once you finish your table, stuff on the far left are the X values of the transform function. Stuff on the far right are the Y values of the transform function. So you can see that here. It went right 1, up 2, and stretched by a factor of 2. On number 4, this time you had a B value. We didn't do a lot of these first semester, so I wanted you to try them. It's on the inside. Insiders lie to you. This says multiply x by 2. That means you divide x's of the parent by 2. Or you might think about it, instead of multiplying by 2, you multiply by the reciprocal, 1/2. So I multiply the x's by the reciprocal, or do the opposite operation instead of multiply, divide. And added my k, added a k value of -2, subtracted 2 from the y's, and plotted. A b value is a horizontal change. It's really the opposite. It's dividing by 2, so you're horizontally compressing values in on the parent. And then finally, number 5 was just playing a little bit with the reflection. If you have a reflection and you're going to use your table, the a value would just be -1. Multiply the y values of the parent by -1. Then subtract 1 for the k. And that's this. Make sure you know what a cubic function looks like that's not been reflected versus one that's been reflected. On 6 through 9, and again, I'm going through these fast. If you need to pause and look at them, just pause the video. Because everybody will want to pause in different places. I'll just leave this up. This was where you had to take the solutions and make factors. The solutions are 0, z1 and z2. You form factors with x minus z1, x minus z2. You can call them roots as well. So x minus and x minus, make sure you subtract every term in the solution when you form the factors. Number 6, I multiplied with distribution and collected like terms to get the equation. 7 was a simple FOILing, which is also distribution, but it was a pretty 2 terms times 2 terms. I just FOILed. Number 8 and number 9, I did box method. remember, if you're going to do box on these, if there's a constant in your solution, there's a constant, it's in the middle of the factor. You want to put it at the end when you're multiplying by box. Put your real number at the end, because then you end up with nice patterns where kind of some of your more complicated terms will have a plus and minus. They're going to add to 0. And if you put your constant at the end, those are going to be on a diagonal from each other. So you can clearly see plus 4i minus 4i is going to add to 0. Remember that I squared is negative 1, so negative I squared is positive 1. I squared is negative 1, so negative I squared is negative negative, which flips to positive 1. And this one had an I and a square root. Remember on square roots, like the square root of 3 times the square root of 3 is just 3. And negative I squared is positive 1 because I squared is negative 1. Alright, you might need to pause the video and really dig into some of that math and operations. Moving on to the second page, this is where you had to factor the equation. Not all of them factored traditional means. So what we did in the notes in class, we did the discriminant first, the stuff under the radical in the quadratic formula, because the discriminant will tell you if you have real or complex solutions. For instance, in this case, the discriminant is negative. In the quadratic formula, I'm going to have a negative square root of 12. That's going to simplify down to 2i root 3. So complex solutions, the quadratic does not factor. So I use the quadratic formula to find the solutions. Negative 3 plus or minus I root 3. Remember, negative 3 plus I root 3 is 1. Negative 3 minus I root 3 is the other solution, or 0. And then factors are x minus z1, x minus z2. Remember, minus the negative 3 is going to flip to positive 3. On number 11, same business, discriminant. This time it was positive, so I have real solutions, but that's not a perfect square. Square root of 76 would be 2 root 19. So I would have a 2 root 19 in the quadratic formula, negative b plus or minus 2 root 19 all over 2 times a, 2 times a. Simplified down, you get this. So I have z1 is 2 plus root 19 over 3, and z2 is 2 minus root 19 over 3. When you write your factors, x minus z1, x minus z2, you have to be really careful distributing the negative on a fraction. You're only supposed to deliver it as to the numerator, not the denominator. You don't want to send it through both, just one, and we usually do the numerator. So if I distribute that negative and took away the parentheses, it would look like this, which could be a little ambiguous for the reader, because if you distribute it back through, you're going to flip the sign again. So be careful on this a little bit, especially when there's a minus in front. If you want to make sure you get it right, make sure you just keep your kind of nested parentheses. Put that fractional 0 inside parentheses, inside the big parentheses for the factor. I'm fine with that. All right, number 12. It actually did factor. The discriminant was 25. That's a perfect square. If your discriminant's a perfect square, the quadratic factors, 2 factors with negative 4 that add to negative 3. 13 was a special case. I just solved with square roots. Solutions are plus or minus 5. So I wrote my factors x minus z1 and x minus z2. If you really look at number 13, if I had set this problem up as x squared minus 25, you might start seeing a relationship between conjugate binomials. When you multiply conjugate binomials, that's what these two things are. The result is a squared minus b squared. X plus 5, x minus 5. The result is x squared minus 25 squared. All right, because that's coming up in a week or so. Again. And then the last two on this page, 6x squared plus 36 is 0. This was another special case I could solve with square roots. I just subtracted the 36 to the other side because it's a quadratic with no b term. If you're missing your b term, you can solve with square roots. It's actually imaginary, though, because I'm taking the square root of negative 6, plus or minus I root 6. So there are my factors. And then the last one. This time the discriminant was 41. It's positive, So the solutions are real, but 41 is not a pretty square, perfect square, and it actually doesn't simplify under the radical. So square root of 41 just stays square root of 41. You get your negative b plus or minus the square root of the discriminant all over 2 times a. This one, when you simplify it down, your zeros, negative 3 plus root 41 over 4 and negative 3 minus root 41 over 4. This time when you distribute the negative through the fraction, this negative distributed to the negative 3 is going to flip it to a positive here. Negative to negative 3 to a positive. You also have to distribute the negative to the second term in the numerator. Second term. And this one I don't mind like here. I don't have the ambiguity I have on number 11. It's more clear than number 11 because there's a plus sign between x and the zeros. Number 11 had the minus sign. If you're confused on that, just leave fractional solutions in parentheses, nested inside your factor. All right, finally, the last page is a word problem. The key to this, it's a projectile being shot from a well, recognizing that when they graph this, the the y-axis is representing height in meters, which means you can treat the x-axis as the ground. So if you treat the x-axis as the ground, the y-axis is your height in meters. Hopefully it starts to come clear that 0.7, remember, your x-axis is measuring the time in seconds. So at 0.7 seconds and 2.8 seconds, those are zeros. 0.7 and 2.8. So I filled those in as my zeros, made factors, x minus z1, x minus z2. Don't forget the negative 4.9 out front, and then I ran to Desmos and graphed it, or looked at the graph. It's a real-world situation where time starts at 0. So I found the y-intercept. That was one of the questions down here, too. So I know where the projectile began its little adventure here, negative 9.604 meters below the ground. It popped up and hit ground level at 0.7, traveled, and then hit the ground again at 2.8 seconds. All those values helped me get a reasonable domain from 0 seconds to 2.8. I had to get the maximum height of the parabola to get a reasonable range, or get the range for this thing. So the maximum of the parabola occurs at x equals 1.750, y is 5.402. So that's the maximum height for my range. Bottom of the well, minimum. The vertex, I just told you before, I had to find the vertex to kind of complete some of this stuff, so I already had that answer. The vertex was the maximal height of that function right here at this value. And when x is measuring time, this tells me at 1.75 seconds, I pretty should put seconds in there. Ooh, I'm going to do it now before I lose points. The projectile reaches its maximum height of 5.402 meters. The y-intercept is at time 0. On these motion problems, that's when the whole system gets into motion. So that's where the projectile is initially shot. And so that distance, or that y value, the height, gives me the height. And notice it's negative, because the well, of course, is dug into the ground. So the projectile is shot from 9.604 meters below ground. Make sure you start getting used to 3 decimal places instead of 2. We've got to transition you from middle school honors to high school AP, honors and AP. We want 3 decimal places. And then finally, the last one, which I think is interesting, if you change the negative 4.9, the a value in the front, if you change it to some different non-zero number, so you can't put it as 0, what changes in the graph? Well, if you change a, for instance, if you just change it positive, the graph is going to now reflect back up over the x-axis, but the roots are always going to stay the same. You can change a to stretch and compress the graph, but if you don't change the roots, the y-intercepts will always remain the same. All right. Again, you can pause the video when you need to. Make sure you mark down any questions. We'll go over them in class the next time we meet. Your next task is to go complete your feedback form. Let me zoom out so you can see this all at once as the video ends. Oops.